This week, we're happy to have Christine Berkesch from University of Minnesota talking on the geometry of toric syzygies. And if you have any questions, feel free to post them in the chat window or Q&A. Thanks, Christine.
Thank you, Claudia. Thank you to all the organizers for having me speak. I'm happy to tell you about this project today. It's going to be actually several projects that I'll mention at various points in time. So my plan for the first half of the talk is to stay rather basic, as I was asked to do. And I want to first tell a story about projective space that should be familiar. But all is not lost, even if it's review, because the goal then is to take that story and then run a parallel story in the toric variety case. So we'll really be going through sort of the same format 2 times, but in 2 different settings. So that's where we'll start out. Let's go ahead and just dive in. We're going to work over some algebraically closed field, K. And we'll start with some background. And maybe before I even say that, I'll just say sort of the takeaway for this whole hour or 45 minutes is that what a minimal free resolution is for projective space is what I will define to be a virtual resolution will be for our smooth projective toric variety. All right, so that's the parallel that we're looking for. So what sorts of things do I want you to think about when it comes to minimal free resolutions in projective space? That's what I want to get at introducing in the background section. So let's start with a point that's in m+1 dimensional affine space, and then look at our torus action given by scaling. So I have some t acting on x, and it's just scaling each coordinate. And so that is there. All right, so then of course we use this action to make projective space, right? So if I take a non-zero vector, I can look at its equivalence class under this action. And this is then the line through the origin containing x, but then deleting the origin. And so then we put these together, view these lines as points, and that gives us m-dimensional projective space. And then of course we have our natural surjection, because we got this by taking the quotient. Okay, and so then if we have this geometric space, and then we want to go over and be able to look at the algebraic side of the algebraic geometry correspondence. So I want to move over to what does it mean then to look at the polynomials on this space as functions. And so let's just point out then that the only way for 2 equivalence classes to be equal here is for them to be scalar multiples of each other. Our orbits are separated here under this quotient. Okay, so this is useful once we move to polynomial functions. So I'm just, for the sake of trying to help quell confusion, let me point out here that I'm always going to use a multi-index notation. So when I write x to the alpha, I will always mean x0 to the alpha 0, the product of the xi's raised to the powers in my vector alpha. And then, of course, the norm function is just the sum over the entries in alpha. Okay. So if I have a polynomial, in my m+1 dimensional polynomial ring, which I'll call S, and I have some point in my projective space, then I can evaluate at the point in my projective space by picking a representative in that equivalence class. And of course, I want this to be well-defined. So when is this well-defined? Well, we need to respect then the torus action that we had. So we need to see that we evaluate the same on all of our points up to scalar multiple. And the way for that to happen is for our polynomial to be homogeneous. So we're going to restrict ourselves to looking at homogeneous polynomials. So if we have some subset in our projective space, I'll write I of x to be the ideal of all polynomials that vanish on those points. In my projective space, or in my x, and then this is the ideal of x, and of course this will be generated by homogeneous forms. This is a homogeneous ideal. And then, just as an example, we'll use this ideal in just a moment. So let's look at the following 5 points, say in P2. So I'll look at first these 3 points that give me the coordinate axes, and then say these as well. Then in this case, I of x is generated by 3 polynomials. So we have 1 polynomial of degree 2 and 2 polynomials of degree 3. Okay, so that's the end of the background. Now I want to talk about something that's still quite old. Let's have Hilbert enter the picture. So looking at my polynomial ring, I have my polynomial ring. Let me fix my notation here. I'm viewing it now as a standard graded polynomial ring. So the degree of every variable is 1. And then I'm in this whole section, I'll be given a standard graded module. So I have some module that has a direct sum decomposition. So this is a finitely generated graded S module. And the Hilbert function for M tells me the dimension as a K-vector space of the dth graded piece of M. And so looking at this function, Hilbert observed that this was a function that eventually became polynomial. So there exists a function I'll call P sub M, a rational polynomial, such that when D is sufficiently large, my polynomial gives me the value of the Hilbert function. Okay, so this is a really beautiful result that gives us a lot of nice, helpful information, even geometric information about the module M. For instance, the cyclic module S mod I of x in the setting we were just looking at. And so to get this theorem, Hilbert went back and used some homological algebra to actually prove this result. So let's just remember or recall what a free resolution is. So we have an acyclic graded free complex, called F. And this is minimal free resolution of M if a few things happen. So we want the 0th homology to be M, and then, right, we already covered acyclic, so our higher homology vanishes, and then we want free modules. They should be graded free modules. So they look like this. And then the minimal part is saying that if I have my differentials, then when I apply them, I have my graded maximal ideal is involved in my entries. So I'm not using units in the entry. Okay, so how does this help us with computing the Hilbert polynomial? Well, it actually, I mean, having a graded complex here is really useful because when you restrict to a single graded degree, then you have a graded or a single complex that's a complex of vector spaces. In this case, then it'll also be cyclic. And so once you have a complex of vector spaces, you can do computations very quickly. So let's go back to our example that we just had, our 5 points. In P2, so if our module is S mod I of X in that setting, then our free resolution, so in the 0th position, we have our S, and then remember our ideal was generated by one form of degree 2, and then 2 forms of degree 3. And if we go back up and look at those to compute syzygies, you can see here, let's see, what did I have? So if I do minus x0, x1 times this first one, and then I add x2 times the second one, I get a syzygy. So that gives me then something that will be, right, a jump of degree 2 from my degree 2 form. So I'm going to have an S minus 4 here to account for that shift in just one of them. And then I'm done. That's enough in this case.
Christine, I think you have an exponent of 2, not 3 there. I mean, yeah.
Okay, good. You're paying attention. Thank you. Okay, so, right, so what can we do? We restrict to a single degree, and then we can start taking alternating sums on the way back. And then if you remember that when we have a large enough inequality here, then the dimension of one of these graded pieces is a polynomial. And so then if we just start taking alternating sums of these as we move back, we've gotten the Hilbert polynomial. Okay, so just moving through our complex, we have this, and this works great to get a polynomial as long as you know that we're finite, so that we have the 0 here, so that we're not taking this alternating sum forever. So that necessitates the need for Hilbert's syzygy theorem, and that's what I want to recall next. So I'm going to call that one and another one actually. So we'll call these classical results. I don't think that's too controversial. Okay, so we'll state this in maybe a slightly non-standard way. But there are.
Can I pause you one more second? So some people are saying there should be another syzygy so that the alternating sum of the ranks is 0. So maybe there are 2 syzygies.
Sorry, there is.
Yeah, okay.
Right, I need something with this. So I need another syzygy that involves this and another one. Yes, thank you. Okay, good. Yes, there is a 2 there, but they're both, yeah, they're both have a twist of -4 there. Good. Okay, so now what do I have? So this has a minimal free resolution of length at most m, right? And I can say m here over projective space because I'm saturated with respect to the graded maximum ideal. Okay, so we have Hilbert's syzygy theorem, which tells us, certifies we get, this, we only have finitely many non-zero modules in our minimal free resolution, and so we're able to compute the Hilbert polynomial and know that computation works. All right, so that's one place, and of course, out of the Hilbert polynomial, we're getting these other geometric invariants, right? We're getting degree, multiplicity, we're getting dimension of varieties. So there's a lot of geometry that's hiding in that polynomial that we're able to compute now from the free resolution. So I want to point out then another theorem that, at least in one form, was started around that time when Berkesch generalized. So if, right, so if x has, maybe I'll say it this way, is such that S mod I of x has a minimal free resolution of the form, so it's short, we have 2 steps with, so we have the equations that define our ideal and then a matrix in the second step. Then we know that our ideal has a certain form, right? So we're taking the maximal minors of our matrix M, and then we're scaling them all by possibly some non-zero divisor. Okay. Okay. Let me give you one more classical result here. And what we need is slightly newer. We need a few more definition recalls here. So let's look at regularity for just a moment. So sticking with M being some finitely generated graded S module, and I'll pick some vector Z, or sorry, some integer P, then I'm going to use a different definition of regularity than Mike used last week. So here we'll say M is P regular if for every integer we have the following. So when R is P minus Q plus 1, we need this local homology module to vanish. So the Q in graded piece R. And then for all R's past P plus 1 and beyond, we need our 0th local homology module supported at the graded maximum ideal to vanish. And of course, for in this standard graded case, if we look at the number of non-zero rows in our Betty table, then this jives with this definition. So Mike's definition last week was from the Betty table. But unfortunately, for what I want to say later in the talk, that definition doesn't work so well for generalization. So this one, but this one does. So that's why we're going to stick with this one for today. And so with this in mind, then I'll give you the other theorem. and that's an equivalent way to think about what it means for a module to be p-regular in terms of the minimal free resolution. Right? So we can take the graded truncation of our module, looking at grade degrees p and above, and this has a minimal free resolution of the form. So we start here, and this is then a linear resolution. So this pattern continues and as long as needed. And then this is equivalent to M being p-regular. All right, so let me pause here for a moment. This is the first half of the first half ending. And we now have this recap of these three classical results for projective space. And so maybe I'll just stop. Are there any questions at this point, or are we good? Now is a good time. Nothing right now, I don't see anything. Okay. So now what I want to do is switch gears and kind of restart and run in parallel to what I've said so far, but now for different spaces. So now's a good point to jump back in if you're looking for that. Okay, so we can kind of call this part B then. So I'll run my numbers the same again. So for our background here, I want to start now with an algebraic torus action. So I need more exponents. So these are going to be vectors in z to the r. And so I'll have an r-dimensional torus acting on capital N-dimensional affine space. And so now these act by scaling via the monomials here. So now t is a vector, a is also a vector, but this is getting a little vector heavy, and so forth. Oh, no. There we go. Okay, and so this also then is t acting on it. Okay. So I'm going to write things in slightly different order, but pretty close. I'll keep it pretty close, but I want the polynomial rings sooner. So now I have my polynomial ring in capital N variables, and I'm going to grade that ring based on the vectors in my torus action. And then inside of here, I can find, I'm going to take a monomial ideal, B, and the way that this comes to me is that I want to pick out the orbits of my action that are not full dimensional. So the variety of B is dictated by the action. And now, right, so B, or the variety of B is playing the role that the origin played for projective space. So these are the things I want to remove before I take a quotient by my action. But first, let's build the quotient space. So I'll take my k to the capital N, and I'll remove this variety of B. And then for such points, I can look at equivalence classes under this action. And so the varieties that I want to work with then are these Toric varieties that come to us in this way. So I have my X, which is these equivalence classes. And then this can be thought of right? So what I'm doing is I'm taking my K to capital N, removing B, and then I'm doing a good quotient by my R-dimensional torus. Okay, and I'm going to assume that I've chosen all my actions so that I end up with a smooth projective variety at the end. All right, so perhaps the easiest example here we could go with is a product of projective spaces. Once I'm moving past a single projective space. So here I just have, I need now 5 copies of my field. And now I'll scale. I'll use my first component of T to scale on the first 2, and the second component to scale. Oops. This is going to jump pages. Oh, but I've been using 1 through. Change my indexing here. 1, 2. There we go. And so in this setup then, my polynomial ring, oops. Oh, what was I doing? No, I was going to change things. Yes, I will, just because it's easier to talk about in my example in a moment. Sorry about that. I'm going to use variables coordinates x0, x1, and then y0, y1, y2 here. So then I have x0, x1, and y0, y1, y2. And then, of course, the b in here, I need to remove the origin, what would correspond to the origin, each of the projective spaces. And my multigrading then is that the degree of the xi's is going to be the vector 1, 0, in z2, and the degree of the yj's is 0, 1. Right, so this is our setup. So now we want to move into the parallels of our minimal free resolution. So now I'll introduce what a virtual resolution is. So pretty much everything else I say, M is going to be a B-saturated, finitely generated Z to the R-graded S module. I guess the B-saturated sometimes I can leave out for this definition, but often I'm going to want B-saturated as we move forward just to make things easier to state. Okay, so a Z to the R-graded free complex. Okay. This is a virtual resolution of M if the following things happen. So, right, first, when I compute zeroth homology, if I saturate with respect to B, this is why I want to be saturated here to make this simpler too. If I saturate with respect to B, I should recover M. If I remove the B saturated on M, then I just saturate both sides. And then for higher homology, I only want to have this irrelevant homology. So only homology that corresponds to this irrelevant locus is allowed. So we're relaxing the condition of being acyclic by allowing ourselves to have this extra homology that's supporting this ideal that geometrically is irrelevant. And so for those who prefer the geometric side, then notice what I'm saying here is that when I sheafify, this is a locally free resolution of the sheaf corresponding to M. Right? And in particular, it's not just any locally free resolution. It's actually a resolution using direct sums of line bundles. So these are very special locally free resolutions. Okay, so with that in mind, it seems like a good time to do a couple of examples. So that's what I want to do next. So let's start now with a collection of 2 points in P1 cross P1. Back things down just a little. So these are like my 2 poles in P1 cross P1. And again, I'll use coordinates X's and Y's on my 2 products. So in this case, let me first give you the minimal free resolution. So I have okay, so this is the minimal free resolution in this case. And now from that, we can actually obtain a few different virtual resolutions. So we're allowing ourselves to have this irrelevant homology. So one of the things we could do is start taking our ideal, intersecting it with components of the irrelevant ideal, and then resolving those. And that gives us some nice complexes here. So first, right, if I intersect with one component of the irrelevant ideal, namely the one for the first set of variables, then I'm throwing away allowing this 0, 2 form. So this is a minimal free resolution of this ideal. And then of course by symmetry I can do the same thing for the other ideal. So I get these. All right, but why not intersect with the whole ideal, right? And in that case, I get something different. So if I just looked at taking the 2, 1, 1 forms, then I actually get this really nice Kazoo complex that comes out. Right? And this is also, so this is the minimal free resolution of the ideal for the points intersected with the irrelevant ideal one time, which is very satisfying. I think, you know, looking at the original ideal, it's not a bad ideal. It's not terribly complicated, but somehow wouldn't you much rather have a Kazoo complex than anything else if you have the choice? Right? So these are 3 options that work in this case. And so one of the things you'll notice right away then, when we had minimal free resolution, those are unique up to isomorphism, right? And we immediately lost that here. So once we move to the world of virtual resolutions, we've lost uniqueness, but we're gaining some other nice things, right? We're gaining here some smaller complexes that are telling us, you know, different pictures of our points in some sense. And in particular here, we're getting this really beautiful complex that's telling us we can actually cut out our points here with just 2 forms in our space. All right, so let's do another example. All right, so now this is a certain curve inside P1 cross P2. Right, and then the minimal free resolution here of S mod I of Y just takes a second to write down, but I think it's worth it to see what's happening here. I'm going to write my vectors the other transpose just to save a little bit of space too. So we have all of these forms generating. and then several syzygies. So this gets much bigger, and this is still quite a small example as far as examples go. And then we're done here at this step. All right, so that is the minimal free resolution for this curve, which is quite big. And trying to read off geometric data from the curve, there's a lot of sum ants here already. And in particular, right, you'll notice my P1 cross P2, so this is a three-dimensional space, and now I'm at length 0, 1, 2, 3, 4. I have a length 4 complex. So, and this is typically going to happen because now I'm going to have many more variables than the dimension of the underlying geometric space, as opposed to projective space where I just had that one extra variable. Okay, but all is not lost. I'll give you here one virtual resolution that works in this setting is what I'll highlight here. In yellow. So it's this 1, 4, 3 complex you see. And right here. So if I just go from this single or from the S minus 3, 3 of those here, I have this 4 by 3 matrix then. This is actually a Hilbert-Birch complex that I get out of this example. So instead of having this huge free resolution, there's actually this really nice Hilbert-Birch complex that also geometrically describes my curve. Okay. All right, so it's getting to be time to state those results. And I have a little visitor here too.
Mom, I can't find me. I don't know, I didn't do it now.
Well, I will help you find your Lego piece a little bit later, but right now I need to keep talking. All right. It's rough when you can't find your Lego piece. Oh boy. All right, so let's go ahead and get to now our virtual results. So what do we know? So this is joint work with Daniel Ehrman and Greg Smith. And these results are all for projective space. So I'm going to write P to the N for P to the N1 cross out to P to the NR. So for every subvariety in my product of projective spaces, my coordinate ring, in this case, has a virtual resolution now of length at most the dimension of my space. All right, so we have a virtual Hilbert-Syzygy type theorem for products of projective spaces. And then next we were looking at Hilbert-Birch. So now, this doesn't work for arbitrary projective spaces at this point, but we have, if X is P1 cross P1, and then we're looking at a collection of points, then we get a Hilbert-Syzygy type theorem. So this has a virtual resolution of the form we would hope for. So this form with J then of course equal to the minors of our M. Right, and then you'll notice once we have any collection of points in P1 cross P1, we also have a theorem like this for P2. And so then if we take an arbitrary toric surface and a general collection of points so that we've missed the exceptional divisors, then we can use this theorem to get results there too. So, okay, so our virtual Hilbert-Birch also holds the theorem. Also holds for X a toric surface and containing some Y collection of general points. Okay. And specifically for P1 cross P1, I just wanted to point out a nice paper of Duarte and Seslianu where they use this free resolution or this virtual resolution to compute residual resultants over P1 cross P1. So that's a really nice consequence of this. And yeah, so using a virtual resolution. Okay. All right, so that gives us the first two theorems, and then last we had the regularity theorem. So I'll finish up this first half with that. And so to do that, I need to just briefly maybe go over multigraded regularity. So again, I'll just stick to our product of projective spaces, and then we have our Cox ring, which is the polynomial ring we've been using. Okay. So when M is now, we're already in the same order, so B saturated, finitely generated, Z to the R graded, S module. Then I'm going to take the definition that goes back to McLagan and Smith that says M is now, so I'm looking at my regularity. This needs to be something in a vector in Z to the R. So M is deregular if, when I look now at local cohomology supported in B in degree P, this is 0 for all I at least 1 and for all vectors P in the following set. So this is this. Okay, and so it's not important that you remember what this definition is. I thought I would write it down for clarity. Notice when I was over a single projective space, I had also a condition on H0, but here because M is B saturated, I can ignore that condition since my H0 is at B will vanish. So just one simplification to write things down a little faster. Okay, so to give you the analog of how deregularity and linearity match up, in this setting, we need one more bit of notation, and that's that I want delta I inside of Z to the R to denote the set of twists of summands in the ith step of the minimal free resolution of S mod B. Okay, so we're just taking the minimal free resolution of S mod B, and Bayer and Sternfels actually computed these a while ago. So delta 0 is going to be the 0 vector, and then for all I at least 1, delta I is the following. So this is these. We have lots of component-wise comparisons of vectors here over certain ranges. Okay, so just those degrees. All right, and so before we solve a projective space, that being regular gave you a nice linear resolution for the truncated module. And we have something similar here then. So we'll fix our vector D, and we're still working over e to the n with m as before. Then m is D regular if and only if. When I take m and twist by D, I have a virtual resolution of the form. This line is not so enlightening, except that it will end at exactly dimension. And then when I look at the summand, the degree of each generator of Fi is in the set delta I plus n to the r. Okay, so instead of having strict linearity, we need to account for the fact that we have our irrelevant ideal B. And so instead of just something that's straight and linear, because we're in this higher dimensional situation now, we need to have these delta i's to kind of spread things out as we move back. So I think that's a good place to stop for the first section. I guess now we have a short break.
Christine, if I can distract you.
Yes, go ahead.
Does the length of the resolution matter in that formula for the regularity in terms of the free resolution or the virtual?
We use that the degrees of the generators need to live in these settings. I'm trying to remember now if we need. Right, we're using that there is a virtual resolution of this form, so that doesn't mean that it certainly doesn't preclude shorter ones, for instance, showing up. But we are using in the proof that we have one of that length of this form.
Yes, what I meant was if you have any virtual resolution and you get a bound for the regularity. This doesn't exist.
Oh, yes. And in fact, did I, yeah, no, so you could also think about this theorem as giving you a way to measure regularity as well, like to find the multigraded regularity set. I guess that's what you're getting at?
Yeah, indeed. Yeah. And in particular, yeah. So if you just find some virtual resolution, for example, the actual resolution, you get a bound, if I understand right.
Yes, let me get back to sharing here so you can see.
And when you're ready with that, there are 2 questions from the audience.
Okay, let's grab them. Oh, I'm sharing. Okay, there we go. Okay, go ahead, David.
So the first question was, could you repeat why the Hilbert basis theorem for toric surfaces follows from the P1 cross P1 case?
Back there. Okay, so if I'm looking at a toric surface, it's going to be a blow up of either P2 or P1 cross P1 at some points. And so if I have general points, I can avoid the exceptional divisors. And so it's kind of cheating to say the theorem works in that setting for those on a toric surface. But I mean, what it is telling you is that they're in that setting, you know, you're essentially looking at something that's happening in P1 cross P1 or P2. Since you've avoided the exceptional divisors. So you can take the theorem in those settings and move it.
He's continuing his question and saying, what about Hertzsprung surfaces? That something is not true then.
Oh yeah, let me think. I have to remember. I don't remember off the top of my head. It's not a problem, but I can't remember why. So I apologize. I'll get back to you, Nathan.
Yes, Nathan. And so he said, okay, thanks. And then Neil asks, is a virtual resolution, is there always a virtual resolution that's obtainable as a direct summand of a minimal graded free resolution?
Great question, Neil. That segues well into some of the things we'll talk about in a little bit. So yeah, there are certain subcomplexes of minimal free resolutions that will always give you virtual resolutions. And that's one of the things I want to tell you about in the second half. Yes, but not
okay.
everything.
I think that's all the questions for now.
Okay. All right, so yeah, so what I want to do with the second half is eventually talk about constructions, but I wanted to tell you about two other results first. So the first is still from my paper with Daniel and Greg, and that actually goes back to our example of the curve. Here's our curve. So we had this nice Hilbert Birch presentation. So one of the things we could do here is look at our matrix phi, and think about that as giving us or corresponding to a point in the Hilbert scheme where this curve would live. And because we have this nice Hilbert Birch presentation, we could now move that point around, right? In particular, we're seeing that this point has to be smooth in that Hilbert scheme. And that works more generally. So I wanted to tell you about that. So this is why I cheated a little bit and started writing, because there's a lot to write here. So let me tell you what I've written here so far so you can process, and then I'll keep filling in. So we're still in a product of projective spaces, and we need one condition here on our ideal. And that's that looking at our generating degrees, we get this isomorphism. Right? And this is so that we can use the Payne-Schlesinger comparison theorem. And then it turns out that if we're in any of the three sort of classical situations where you would want to have an unobstructed deformation theory, things work nicely here too. So the first one is that we're in a codimension 2 setting, and then we have a virtual resolution that has length 2, right? And what I haven't told you about is this VRes pair. And this is a coming attraction. So I'll tell you what this specific construction is. But there's a certain virtual resolution that when it has length 2, like the curve in the example, then we fall into this setting. Similarly, if we're in codimension 3 and we have length 3 with the self-dual complex, or if we're in arbitrary codimension, but then we have that this VRes pair that I'll tell you about soon is a Cazole complex. Then the embedded deformation theory of Y is unobstructed. So we're getting these really nice smooth points. So I really like this theorem because I think it takes us one step beyond what we saw in the first half, and we're seeing some really strong geometric consequences coming from this homological property. Right? So going back to the takeaway I said at the beginning was that we want to think about what minimal free resolutions do for us over projective space. We want to think about virtual resolutions doing that over a toric variety, and certainly this theorem is giving us a strong comparison to that regard, like the three previous theorems did as well. All right, and then one more parallel I want to tell you about is not my theorem, but my students. And this goes back to the work of Buxbaum and Eisenbud on what makes a complex exact. So hopefully this is a favorite theorem of many in the audience. I wouldn't be surprised. So all right, so when we have a graded free chain complex, let's say it's length t. So over in this case, I'm going to think about my m-dimensional projective space here. This is exact if and only if, right, both of the following hold. So first we have our rank condition with the ranks of 2 consecutive PIs add up to the rank of the intermediate module, and then the depth condition. And here the I of phi I, right, these are the rank size minors. These should be at least I. So again, a theorem that has given us a lot of mileage over the years over when we're working with a standard graded setting. And so what Mike was able to do is ask the question, instead of exact, what makes a complex, right, a virtual resolution of something. And so same hypotheses, but now we're going to work over our smooth projective toric variety, and then say this is virtual, or a virtual resolution if you like. And the only thing we need to add here is this up to saturation. Right, so the rank condition stays the same, perhaps not surprising, but then we need to worry about our minors only up to saturation, because of course the geometrically irrelevant part shouldn't be factoring into this. All right, so yet another example of minimal free resolutions on projective space now porting over to the virtual world, and virtual resolutions taking their role there in this setting. All right, so with those in hand, now I want to move really to telling you how we might get our hands on some of these. So I'll spend the rest of the time telling you about a few different constructions, like ways to make virtual resolutions, and then finish up with a few open questions at the end. Okay, so, all right, so we'll be in the setting either of products of projective spaces or an arbitrary X throughout. And in either case, M will always be our B-saturated module. So of course, the 0th construction, I just want to mention, this is the naive idea, right? And that's simply to insert by, say, intersection or similar means, extra primary components that are components of the irrelevant ideal, right? So insert components of B into the image of some phi I, right? And then you could say resolve the tail and then continue iterating this kind of process, move back and continue. And so this would be a way to kind of take a minimal free resolution, or at least take your module and generators, and you could add some homology and see, you know, as you move back, you're not getting something acyclic. Sometimes this is beneficial, like we saw, you know, when we intersected in our examples with different components of B, we were getting some smaller things. So sometimes you can get some mileage out of it. Sometimes powers are interesting, give you different constructions. But there's certainly more to the story than that. So we're going to move on to other things here. Okay, so the first one we'll talk about here is the resolution of the diagonal. And so this actually takes us back to the virtual Hilbert-Syzygy theorem. This is what we use in that proof. So to prove that we have this upper bound on length, for some virtual resolution, we actually construct a specific resolution in this way. So here we're working with our product of projective spaces. And so this is, you know, when we want to resolve the diagonal, we start with our Cazul complex. But now we're in this multi-graded setting. Okay, and so we have these box products. So these are just tensors of pullbacks from the pieces of the products with twists, right? Where here our cotangent bundle, we're just, should be careful here, right? Our cotangent bundle now is just this box product of the cotangent bundles from the pieces, right? And then the AI twist, maybe I'll add, this is, then you could twist each one individually, right? Okay, so, all right, so then what we want to do is look at X cross X, and we have our two projections, which I'll call P and Q. No, I'm going to call them pi 1 and pi 2. Okay, and then what I want to do is be a twist off high enough to kill off some higher cohomology of a twist of my module. So I'm going to say for a D that's large enough, we want to consider, you know, something that looks like this. So this is the standard Fourier-Mukai trick. So take our Cazul complex. So we're taking our M, twisting it, and we want to, and the D then we want to choose so that it's high enough to kill off the higher cohomology for our twist of M. And then we're going to pull it back, and then tensor with the Cazul complex, push forward to the other product. Right? Very standard trick. And so if you play with this and analyze the hypercohomology spectral sequence you get from this, then, you know, after this procedure, you get a virtual resolution that pops out. Okay? So M has a virtual resolution F with, and then what comes out is this, which I'll just write out. So I want to make a comment about it. So all right, there we go. So this is what comes out at the end of the spectral sequence. Okay, so we have a lot of non-zero cohomology modules that are showing up here. And so in particular, you're seeing these FIs have, right, in this range here, we're getting a lot of non-zero Betti numbers, okay? So in the first examples I was showing you virtual resolutions, we were taking the minimal free resolution and kind of trimming it, and then finding these little virtual resolutions that lived there. this is not that sort of thing, right? Here I'm taking my module and then I'm doing this process that gives me this complex that happens to be short, but now it's really fat, right? It's like short and wide. I have all these modules that are showing up in each homological degree. So it's probably not the virtual resolution that you want to be keeping around in your back pocket and pulling out to do a lot of computations with, but it's a nice construction to get the shortness, right? Because you can see the dimension of the space, this n is built in nicely there to give us that stopping point, right? So the way that we're getting this virtual Hilbert syzygy theorem then is using this resolution of the diagonal to keep things short as we compute. Okay, all right. So I promised you I would tell you about virtual resolutions of the pair that I referenced in the theorem. So let's do that next. Okay, so this is also for products. So what is this going to be? Well, I'm going to take the subcomp. So VRes, the pair of M, and D is going to be, again, some degree rating vector. So this will go with, so the pair is my module and then some degree choice. So this is the subcomplex of a minimal free resolution of M with summands generated in degrees at most D plus N. Okay, so I'm looking at which degrees my summands are generated in, and I only keep them if they're at most D plus N, and if they're not comparable or they're bigger, they're thrown out. Okay, and so actually, if we go back, I hate to do this, but I am going to scroll back up so that we can look at some examples without rewriting them. So we can look here, and you see that actually we could think of this as VRes pair for S mod I of Z and the vector 1, 0 plus 1, 1. Right, so that everything here is less than or equal to the vector 2, 1. And then similarly here, this is VRes pair for the vector 0, 1 plus 1, 1. Okay, and then actually here as well, so this is the way that I got this is I did VRes pair for S mod I of Y for the vector 4, 1, which happens to be in multigraded regularity here. Okay. So if you look at these now, you'll see right, everything here is at most 5, 3, and the things left behind are not comparable. All right, so I'll make that go back to where I was. So what we found here is that if D, or if M is D regular, then VRes pair is a virtual resolution of M. Okay, and the idea here really is to look at the co-kernel when we look at this inclusion. So I have my VRes pair, and that includes into my minimal free resolution, and then I get some co-kernel. Okay, and then you want to show that this has all irrelevant homology. Okay, so really you want to examine in valence and window sorts of twists. So look in a certain range of twists and show that everything vanishes there in homology, and then you get irrelevance. Right. So next, I want to look at monomial ideals and just tell you some other recent work that's been done. So J. Yang has the following. So now in arbitrary X, we can get a sort of Hilbert-Syzygy theorem, a virtual Hilbert-Syzygy theorem for monomial ideals. Okay, so if I is not the whole ring and is B saturated, monomial ideal, then there is a virtual resolution of S mod I of length at most the dimension of X. Okay, so we still don't have a virtual Hilbert-Syzygy theorem in general, but we do now for at least this nice class of ideals. And the construction is really beautiful. So Jay uses a cellular resolution that he builds up of S mod I and shows that that is a virtual resolution, or actually a resolution of a B-saturated equivalent ideal. But then that's actually still too long. So it's still one too long. But then he has this nice kind of projection that he does on the underlying cell and uses that to ultimately create an ideal that has the same, that saturates to I, but does have this shorter projective dimension. So the complex that he's producing here is actually acyclic. It's just resolving a different ideal. So that's what he's able to do there. And okay, so then one other project here. So these are some undergrads that worked with me last summer. And they were looking at not sort of a Hilbert-Syzygy type theorem, but starting to think about Cohen-Macauliness in a virtual sense. And so if we start, they were looking at the square-free case. So if we start with a simplicial complex, that's pure and balanced. So what that means is now I'm working again in the product of projective space cases. So balanced means that every product, or each product in my P to the N is involved in each facet, right? So each facet touches or involves each PNI. Okay, so in that case, then it turns out that you can actually find a virtual resolution for the Stanley-Reisner ring of length equal to the codimension of S mod I delta. So in that sense, I like to think of that as being virtually Cohen-Macaulay then. And that maybe the free resolution could be quite a bit longer, but once you move to the virtual world and add irrelevant homology, then you can find something that shortens all the way down to the minimum possible. And the way that they do that is actually, again, this virtual resolution is acyclic. So they start with the pure complex, or their simplicial complex, throw in irrelevant faces, and then produce a shelling of that complex that they're able to use the shelling to get Cohen-Macauliness for the new simplicial complex. So that's how that works. Okay. All right. Okay, so here's another one that hasn't shown up in a paper yet, but will at some point soon. And that's using a mapping cone to fold in some irrelevant homology and decrease some length. So if I start now with my minimal free resolution of M, say of length T, And I know that my last X module is irrelevant, fully irrelevant. Then I can use that. Let's see, I'll read Megan's question in a minute. Okay, so I can dualize my F to get something that looks like this. T minus 2. Okay, and then I can just take this last map, right, duplicate it, but then resolve. So this is, I'm just doing the indexing this way for my own sanity. Right, but the point is that here I'm resolving, and if as I move back, if I get to the point where, so this is G minus G0, right, so if I'm lucky enough, if this is 0, so if my, if this matrix, this VT star has a short enough resolution, then I can use these equal signs to take my induced maps here, right, and take the mapping cone, right? So what was I calling these? Calling these alpha T minus 1 star, T minus 2 star, right? So what do I get?
Just to interrupt you for a second, is this over toric varieties or products of projective spaces at this point?
This is anything. This is anything. Yeah. So any X. The key here is to get the 0, which doesn't always happen.
And there's a longer question which you saw for later, maybe. Yes. Okay.
We'll give it a second.
Yeah.
Okay. So what do I get then? Right. So I can use my mapping cones to say then that the cone, if I dualize, take the mapping cone, cone of alpha, right, is V res of M. That minimizes down to something that looks like this. And so forth. And as I minimize down, because I had equal signs there at the tail, I'm getting this. This should be a 3, and then GT minus 2. So I like this because this is the first time we're seeing the rank of the 0th module in the resolution changing, right? So even though we're starting with a free resolution, we're doing something that's changing that 0th module, which is giving us some extra freedom that produces some interesting resolutions that we weren't seeing using the other things that we had so far. Okay. And this is also nice because I didn't need to use anywhere that M was B saturated. So as long as I still have irrelevant X at the tail, I can iterate while things are working out. That's really helpful. Okay, and for the sake of time here, let me see, I'll just say a little bit about points, and then we'll close out with these open questions. So there's one other construction that Daniel and Greg and I have in our paper about that works for points. That just goes back to intersections. But it's nice because it gives us some shortness again that we don't see, and we can't always prove in other cases, I should say. Right, so if I have some 0-dimensional subscheme, and I'll set I to be I of Z, then there's actually some A in n to the R with the last component, say 0, such that if I do the minimal free resolution of S where I intersect with B, right, and I think about, so when I write B to the A, I'm taking B, I'm looking at its primary decomposition, or prime decomposition into the components corresponding to projective spaces, and then I'm taking, the A-ith power on the ith component here. So this ideal has projective dimension equal to dimension. So it has length equal to the dimension of the space. Okay, and moreover then, anytime you have this AR equals 0 and you take the other AI sufficiently positive, that will be something that works. Okay, you might be cranking up your Betty numbers in the resolution as you do that, but you will get something short. Okay. Okay, and then without stating, I'm not going to state the results now, but I'll just point out that there's this other paper, students from another RU who worked with Mike as well that summer, and that's looking at points in P1 cross P1 and asking, you know, not about virtual clone Macauliness, because now, right, we're expecting, you know, length 2 will give us virtually clone Macaulay, so we already have that in this setting. But thinking more towards complete intersections. So asking, for instance, when do we have a Kazoo complex that resolves our points? And so they have some conditions on the points for when this does happen and when this does not, right? So asking about virtual complete intersection. So there's some sufficient and some necessary conditions in that case that are worked out. All right, so let me just finish up here then by noting a couple of open problems that probably have become apparent as I've been talking the last little bit here. And that's, I'm particularly curious to see some people try to better understand now these other properties of modules that have, you know, tell us, you know, that you have some nice free resolution in the standard graded case. So things like being Gorenstein. So what would it mean to be virtually Gorenstein? Do you have a virtual resolution? You know, right? Is it self-dual of the right, you know, the right length? Like what does that mean? And you know, because there's so many ways we could think about Gorenstein. What's, you know, if we take going from a free resolution, like, can we get a virtual analog here? And then of course, virtual clone Macaulay, we've already made some more headway on, but I think there's a lot there to understand. And then virtual complete intersection seems to be a lot trickier. Getting Kazoo complexes is not so easy. Maybe you only want to ask that the ideal is generated by codimension many forms, for instance, looking at ideals, and not force that it then form a Kazoo complex. There are different ways you can go about that as well. So for all three of these, really making sure we have the correct definition way to think about it, and then figuring out criterion for when these things actually happen. Since now, you know, this world of virtual resolutions is so huge, it's not the same as minimal resolutions where we can go in and just compute it and find out what's happening. There are lots of different ways we could get our hands on them. So not only getting definitions, but also sort of be like tests to get to these and understand what they mean. And another big thing here is back to looking at these Hilbert-Syzygies theorems. Right now we have this virtual Hilbert-Syzygies theorem for products of projective spaces, and we have it for monomial ideals in general, but that leaves a lot of territory uncovered. And so I think this is maybe another direction soon that we should be trying to get some answers. All right, so I think I will stop there. Thank you all for your attention.
Thank you very much, Christine. There's already one question, so shall I go ahead and ask it?
Sure, go ahead.
Yeah, I'm going to say it out loud so that it's on the recording. So if one starts with a sheaf on the variety and surjects onto it from a large direct sum of negative enough twists of a very ample line bundle corresponding to high enough sections of the sheaf, and continue like this, would it give a short sheaf resolution, which gives us a virtual resolution on the level of modules?
Without the high enough twists, I would say no. I think, I'm not sure that I know if we just did high enough, if we would always get short that I'm not so sure. I think there's a tension here between resolutions by vector bundles and resolutions by direct sums of line bundles, right? And so if we were using, if we allow ourselves to also have vector bundles, then of course we can get short enough. But with direct sums of line bundles, things get a little messier, and I'm not quite sure what would happen. This is maybe part of why I'm interested in this, actually, is that I think this is really interesting that there is this difference, and trying to resolve that is something I'd really like to see happen.
Are there any other questions? There are a lot of thank yous.
All right.
So could I ask a question, actually? I think you may have answered it with your example, but I might as well say it explicitly. Is there therefore no sense of a minimal virtual projective resolution?
Yes and no. I mean, there's certainly codimension is still going to come into play in bounding minimal length. So you can have minimal length. And so, I mean, in the examples we had, right, I like to think of these three that I wrote down for these 2 points as kind of the minimal ones, whatever that means, since, right, it's not super well defined, but somehow these are the smallest, shortest ones that are out there. So I would think of these three as kind of being the minimal ones. Maybe I should say here, the regularity here is, if we look in the orthent, we're missing the origin, but then we have all of these. And so this v-res of a pair, like this is somehow coming from this point, and this is coming from this point. And then this maybe you could think of maybe as being that inner corner in some way. So there is some sense I like to think of, especially with this v-res of a pair, that the multi-regularity is telling you something about the minimal ones.
Thank you.
Yeah.
I don't see any other questions.
Thank you for moderating.
Okay. I think there aren't any more questions. So
Thank you, Christine.
yeah, thank you very much.
Take care. Thank you so much.